Hello, this is Concrete Path and the lecture for this one, that's design of pre-stress concrete beams. That we can say that's design of PSC. Design of PSC beams. Design of PSC beams. What this means? What this means? Let's take that you have a simply support beam. You have a simply support beam, and your demand is that I have to fix a length. My length is fixed. Okay, my length is fixed, and I know how much loads I have to apply. I know that how much loads I have to apply for given loading conditions for a given length of the beam, and I know that my material is having some permissible stresses, sigma C, sigma T, that sigma compression and sigma tensile. So these are your permissible stresses for the material. Permissible stresses for your material. And we are also having that steel. Let's say we're having steel stress in the steel, some P naught. And now we need to say, what should we design? I would say you have to design now a cross section which can resist to those moments and all that stuff. You should design B comma D. Its eccentricity of that P force should be located at somewhere, and its eccentricity. We have to design all these, and what should be the area of the steel? What should be the area of that? Those we can say those wires, strands. What should be the area of those? This is your design of that PSC being related to for given loading conditions, and for your permissible stresses. So we have to get the design of that. And for and I would say the design is based on three different classes of those beams. So we have three different classes of your Prestress beams: class 1, class 2, class 3. Class 1 of the beams that says I want no tensile stresses anywhere. I want no tensile stresses anywhere. Tensile stresses should be 0. Tensile stresses should be 0. That means no tension, no cracking. No tension, no cracking. That means full section is having, that means entire section is having C force only. Entire section is having only C force. Second condition is that I am allowing a minor tension. That's small bit, a little bit of tension I am allowing. That's FT can be allowed up to 3 megapascals. Up to 3 megapascals we can allow. Up to 3 megapascals. That's tensile stress we can allow up to 3 megapascals. That we can call as minor tension. Minor tension allowed. But the cracking is not allowed. So cracking is not allowed. And third one is that we're allowing the tensile stresses up to the flexural strength, up to the FCR. We're allowing the stresses up to the flexural strength, and because of this, there would be cracking also developed. Little bit of cracking, I would say minor cracking is also allowed. Minor cracking is also allowed in this case. Okay. So let's take the first one. Let's take the first condition. Let's take the first case. Let's try to have a design for the first case. That's class 1 PSC beams. Class 1 PSC beams. In that case, I want tensile stresses to be 0, no tensile stresses. So we have two different stages of those stress analysis. If I talk about that transfer stage, that is the initial stage when we transfer pre-stress from steel to concrete. That's transfer stage. So I would say let's talk about that section. You have some eccentricity of P, you have some eccentricity of E, and the pre-stress force is P. P naught we can write P naught, and because of that we are having some stresses of P naught by A. One more is there, negative positive P naught E by Z. We are designing for the symmetric section. We are actually calculating for the symmetric section. P naught E by Z, and third one is here because of the dead load we can have. Because of the dead load. M dead by Z, I can say. M dead by Z. So that final stress at the initial, what is the ideal stress condition? What is the ideal stress condition at the transfer stage? That means our tensile stresses should be there. Our net tensile stress at the top should not be there. That means stress at the top should be 0. Net value of tensile stress at the top should be 0. This is the ideal stress condition. ideal stress condition of the first case, that is transfer stage. And because this is ideal stress condition, and this is also corresponding to that class A condition, class A PSE beam, because I want that tensile stress to be 0. I don't want any tensile stress at the top. This is your class 1. Also, we can say ideal stress condition is also corresponding to class 1. So your tensile stress here is 0. So I can have the equation, and I can have the equation that I can write the equation. I can write the equation that F at top, stress is at the top, stress is at the top. This one is your tensile. This is not top. This is your tensile, F tensile, and this is F top, F top, and that means we have P naught by A, then minus P naught E by Z. After that, md by Z plus that should be equals to 0, and stresses at the bottom. Stresses at the bottom is equals to P naught by A plus P naught E by Z minus m dead by Z. That should be equals to some value of Fc. We are allowing some Fc here as per the permissible stresses in the concrete. Let's say here we have some Fc here as per the stresses, permissible stresses in the concrete. Let's say this is the Fc. Let's say this is the Fc. This is positive compressive, and this is these we have two equations for the transfer stage, and similarly we can have two equations for the final stage also. Let's try to go for the final stage. Let's try to go for the final stage. Final stage. So at the final stage, I would say your force final would be equals to K times P naught, and there would be some live load also. There would be some live load also. Because of that, I can write we have m dead plus m live, m dead plus m live equals to m all. I can write that is m all. So based on that, I can say this was your section. There was some eccentricity of E, P was there, and I can say this is P final. So your stresses would be P final by A. After that, one more is there, top tensile, bottom compressive, P final E by Z. Third is because of all those moments, so I can write that M all by Z. And net value, we can say for the final, what is the ideal stress condition? For the final stage, our final stress ideal stress condition is that I want tensile stresses here 0. For the class 1, I want tensile stresses to be 0, and there would be some permissible concrete stress in the compression. So this is your condition for that. Let's write the equation. Let's write the equation. I would say that PF, and we can write that PF in terms of K times P naught. So I would say K times P naught by A, one more is there, minus K times P naught E by Z. We are calculating at the top, and at the top, and that equals to Fc. And similarly from the bottom, we can write K times P naught by A. After that, K times P naught E by Z. After that, minus times M all by Z equals to 0. Okay. Now we can have those. We can keep these equations. We can see whether we can have anything that we can do. Let's remove this part here. So I can have 4 equations. Now we need to do something in order to get some equations. So we are having some equations of. Let's have the second equation. Let's multiply it with K times. For the entire equation, we are multiplying it K times. Then we are going to add with the fourth equation. Let's say this is equation 1, equation 2, equation 3, equation 4. Adding K2 and plus 4 times. Adding these two equations. So I can write K times P naught by A plus K times P naught E by Z minus K times MD by Z. This is your right side. This is your I can say left side, and I am adding this part also on this side. So this is K times P naught by A. That one more is there, K times P naught E by Z minus K times M A by Z. Yeah, it's not K times, it is only M times. This is M times, and that's equals to Fc plus 0. So is there anything that gets cancelled? Is there anything that can get cancelled? So actually we should subtract those. I think we should subtract those. Let's subtract those. Let's subtract those. I would say K2 then minus 4. Equation of K2 minus equation 4. So I would say first one is your K times 2, K times 2, then equation 4 equation we have to subtract. This part we have to subtract. Then we have, I would say FC minus 0. Besides that, finally I can write your this part goes outside, this part goes cancelled, this goes out, this goes out. So you're left with minus times kmd by z minus and minus, that becomes plus ma by z equals to fc. So your, I would say z becomes equals to ma kamad by kfc, ma kamad by fc. This is your equation that we derived. Ma kamad by kfc, ma kamad by kfc. That's your z. What is the section modulus required? That is equals to ma kamad by kfc. It should be kfc because we have multiplied that k here. We have multiplied that k for this equation, k times fc. So this should be k times fc. This should be k times fc. So this is one of the equation we have. Let's try to get one more equation. We say that equation 1 multiplied by, second part is that we multiply equation 1 with the factor of that k, then we subtract equation 4, and from that when we add that, so this becomes k times p naught, and that thing, this becomes k times that, and we have this equation 4, and I would say we are subtracting, so if this part goes outside, this goes out, this goes out, this goes out, and we are left with m dead plus m all. So actually what we are doing, equation 1 into k minus equation 4, so that we get that, we derive finally a relation here. We derive a relation that's e equals to ma kamad by tukpo, This is your equation that we derive, ma kamad by tukpo. And one more thing is there we can derive. One more thing is that if we add that f top plus f bottom, if we add f top plus f bottom from first equation, first and second, if we add those two, I would say we can get 2 times p naught by a, and I would say this one and this one goes outside, this one and this one goes outside, so that becomes fc. So your p force that should that you have to apply, that's equals to permissible stress in the concrete into area of the cross section divided by 2. This is one more equation. So these are your three resultant final equations that you can design for this class 1 pre-stress concrete beams. These are your standard 3 equations for the pre-stress concrete beams. We have to design a pre-stress concrete beam with the live load of 80 kN, and the length is that simply supported 20 meters, and we have to design it as a class 1. Percentage losses we have 20%, 20, and we have to design that. Design means get the values of E, P, B, D, Z, AST, area of the steel. This is your design. And we have to design a rectangular section. This is also mentioned to design a rectangular pre-stress concrete beam. Rectangular. Okay. Then one more condition is that this is your for given loading condition, and for given stresses, permissible stresses of Fc 25 megapascal and F tensile equals to 0 megapascal. Okay. Compressive stress 25, tensile stress 0, and stresses in the steel, permissible stresses in the steel is 1500 megapascal. Permissible stress in the steel is 1500 megapascal. Okay, for this condition we had to design. So since this is a class 1 condition, can I say one of the thing is there, I can say your pre-stress force that we have to apply, that's AFC by 2 based on the equation we have, that is AFC by 2 and A, but we don't know the value of A, so we have to assume the dimensions B comma D. So how can we start that? That means we have to assume something that after that we can change, we can modify accordingly. So if I assume some values, I would say let's try to assume some values. So we need to assume some values for these conditions. We need to assume some values. Let's select a beam of dimensions 500 cross 800. 500 cross 800. Let's say the total depth of the beam is 800 and what you call as width is 500. So D equals to 800, B equals to 500. Let's assume it. And based on the equations we have, based on the equations that what was the section modulus required? That was ma kamad by KFC. Was it ma kamad by KFC? Ma kamad by KFC, yeah. Ma kamad by KFC. So this is your equation. So I know the value of that live load, but I don't know the value of dead load. So once I have assumed some value, of m, once I assumed the section, so that means dead load can be solved as, your dead load would be solved as 25. We can take a gamma as 25. Let's take gamma as 25 into 0.8 into 0.5. That is 10 kilonewton. That's 10 kilonewton per meter. And because of that, you can say dead load moment. Because of the dead load, you can have moment of WL square by 8. Your L is 20, so WL square by 8. WL square by 8. That is MD equals to 500 kilonewton meter. Similarly, your live load would be, your live load was 80 kilonewton per meter. So your live load would be accordingly equals to 4,000. 4500 kilonewton meters. So finally, I would say your all moments is equals to, yeah, that was 4,000. This one is your 4,000, such that all moments is equals to 4500 kilonewton meters. So this is the all moments we have. So we can substitute those values here, and we would say what is the Z required we can take. I would say 4500 minus K times, your value of K was actually percentage loss, 1 minus percentage loss, so 1 minus 20%, so that's 20% here. So I can say 80% is left, so 0.8. And MD is your 500 kilonewton meter, and you have this K and FC. What is the permissible stress in the concrete? FC 25 megapascals, and at the top we have kilonewton meters. So you can get the value of Z required. Z required is coming to be some value 0.205 meter cube, and we have assumed some values of B and D. Now I would say that should be equals to BD square by 6. But now we have two variables. If I fix now this one, let's say that 500 is fixed as B. If I say this is fixed, now I would say what should be the value of D required. So D required should be equals to 6 times 0.205 divided by 500, that is 0.5, then root of that. So D required would be equals to, 1568.4 millimeters. So I would say your depth required is almost 3 times that 500. This is almost equal to 3 times B. So we need to change both the dimensions. That means it's not correct. Your assumption is not correct. So we had to assume such that some values would be there more. Let's take some values of B equals to 800 and value of D equals to 1000. Let's take this value now. Let's solve for this one. Calculate the dead load because of this. Now, second condition. So that is 25 into 1 into 0.8, and that is 20 kilonewton per meter. And because of that, you had you had dead load of 1000 kilonewton meter, 1000 kilonewton meter, and your live load plus dead load is equals to finally 5000 kilonewton meter. So you can solve section modulus Z equals to section modulus would be equals to section modulus would be equals to and that section modulus would be equals to 5000, that's MA minus K times MD divided by KFC 25, and you had to keep this those units accordingly, and Z comes to be equals to 210 10 to the power 6 millimeter power 3. So your if I now fix that B, if I fix that B, I would say B I have fixed it as 800. I want to see what is the D required. We can say BD squared by 6. So I would say your D required is coming to be equals to D required is coming out to be equals to 1254.9 millimeters. So that means we have assumed 1000 value of D. That means D required is more. So we have to take one more trial. That let's go for that section such that your width is now 800, but we are going to increase it by the depth such that it is equals to 1300. Let's calculate for 1300 now. I would say your dead load would be equals to 25 into 1.3 into 0.8. That is equals to 26 kilonewton meter. Because of that, your dead load is coming out to be equals to 1300 kilonewton meters, and live load we already know that was 4000. So your final M all equals to 5300 kilonewton meters. So let's solve for that Z. So Z required equals to MA minus KMD minus KMD minus KMD minus KMD divided by KFC. Okay. KFC. Okay, that means your Z required equals to Z required is coming to be some value, is coming out to be some value such that I would say let's fix the B now. So I would say this is B times this was 800, and there is some D required square by 6. So finally your D required is coming to be equals to your D required is coming out to be equals to 1263.9 millimeters. So this part we have, that means we have assumed some value that was more. So our D was assumed more. So I can say this is less than D provided. So I can say what we can say. Okay, be happy. So let's select that final dimensions of the beam as this one. This is your final dimensions of the beam, and let's go further for the following all other data that we need to design. So once we got the dimensions of the beam, now we need to say what should be the value of Prestress force we have to apply. Is that AFC by 2? 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 So you can say what is the P naught we can have? That is 13,000 kilonewton. 13,000 kilonewton. And what was the one more thing we had to design? That was the eccentricity of that Prestress force P. That's eccentricity was equals to Mach Kamat by Tukpo. Mach Kamat by Tukpo. Mach Kamat by Tukpo. Mach Kamat by Tukpo. Is what was what? Yeah, it's Mach Kamat by Tukpo. So we can substitute those values. Your final values of MA, that is 5300 kilonewton meter plus your losses of 0.8 into dead load of 1300. Mach Kamat by Tukpo 0.8 into what is the P naught? That is 13. That is 13,000 kilonewton, and at the top we had kilonewton meter. So your eccentricity is coming to be 304.8 millimeters below the neutral axis. So finally I would say you had the cross section. There is a neutral axis, and this is 400, and this is also 400. No, this is total of 1300. I would say this is total of 1300, and bottom is base is 800. Base is 800 millimeters, and you are applying some Prestress force of P naught somewhere here. prestress force of P naught, and the eccentricity we got as eccentricity was 304.8 millimeters, and the prestress force was 13,000 kilonewton. 13,000 kilonewton. So now, corresponding to this condition, now we want to verify it for two different stages of the. Now we want to verify this one whether the stresses are within the limits or not. So for this condition, we want to see whether what is the total stresses we can have on the extreme fibers. I would say one of the value is P naught by A. If we talk about the first stage, that is transfer stage. If I calculate for the transfer stage, that means we have to write P naught by A. After that we have minus plus P naught E by Z. Third one is there. What's the third one we have? That's because of the dead load. Because of the dead load we have MD, that was 1300. So I would write M dead by Z. So let's calculate the stresses at the top and at the bottom. So stresses at the top coming to be equals to P naught by area of the cross section, then minus P naught into eccentricity. What was your eccentricity? 3048. That means 3048 meters divided by section modulus of BD cube by 6, BD square by 6 meter cube. And third one is there, M dead is 1300 kilonewton meters divided by section modulus of BD square by 6. This is meter cube. So those stresses coming to be equals to stresses at the top 5.26 megapascal, and stresses at the bottom would be this one is your same value. After that we have this plus, we have this value of plus. After that we have third value of negative. So finally stresses at the bottom comes to be equals to 24.3 megapascal. And this is talking about the first stage, that is the transfer stage. And what is the ideal stress condition for this first case? Talking about the class A, this should be the case. And what we got? We got the case that we have some 5.26 megapascals, and we have some values of 24.3 megapascals. And this was your ideal condition. That stresses should be the tensile stresses should not be there. That it was the ideal condition, critical ideal condition. FC was 25 megapascals. So our stresses got, I would say, your top stress, that was, there was a chance of it to be tensile, but we don't got any tensile. That means it's safe. This is greater than 0. I can say this is greater than 0. That means no tensile. This is not tensile stress. It's not tensile stress, so safe. Okay. And what about this one? This one is your compressive, but it should be within the limits. Your maximum limit is that you can have 25, but you have 24.3. That means less than FC. Then we can say okay. So for the first case we have safe design. Our design is safe for the first case, for the first permissible stresses, that is first transfer stage. Now we have to calculate now for the final stage. So at the final stage we have loss of that 20%, such that your remaining percentage of the those stresses is 80%. So let's try to have that. I would say you're applying some KP naught, such that all this stuff is same, but only thing that's changing, that you have to multiply here 0.8, and accordingly the sign gets changed for the top and bottom. So you have to multiply here 0.8, and the third part we have to remove, and we have to place all those loads. M all we have to write here. So this is your 5300. Your all moments was equals to 5300. This is M all. So we have to write there M all. This was your M all. So we can write here M all. This is equals to 5300 kilonewton meter. So accordingly I can solve further. And your stresses at the coming out to be equals to, let's have the stresses at the top and bottom. Stresses at the top comes to be 18.436 and stress is at the bottom 6.56, 6.56, 6.56 megapascal. This is our final stress diagram for the final stage, for the final stage. And what is the ideal condition for the class 1? What is the ideal stress condition for the class 1? That means FC should be there equals to that 25 megapascal, and tensile stress should be 0. Here the tensile stress should be 0. So this is the condition ideal. And comparing with that, I would say your FC actually is less than the design permissible stress. That's okay. And your tensile stress is not there. That means it is also safe. Okay. So that means your design final is also safe. Okay. So one more thing is there. Now we have that what you call as we have the class 2 and class 3, where we are combining the class 1, class 2 and class 3. Class 2 and class 3 we are combining because there is some it's allowing some tensile stresses. It's allowing some tensile stress on both the transfer stages. So on both the stages, it's allowing some tensile stresses. So some tensile stress is allowed. FT is allowed up to some limit in both the cases. One is allowing some up to 3 megapascals, and one other is allowing up to FCR 0.7 FCK. So that means it's allowing some tensile stresses. So that's why we're keeping it as the same for the we're designing both the classes together. Let's take that. That means for the first case, for the transfer stage, your stress condition should be such that at the top we have some tensile stresses and at the bottom we have some FC. So we have some tensile stresses at the top, negative, and we have some compressive FC at the bottom. And similarly at the final stage, or we can say service stage or working stage, at that condition we can have some tensile stresses at the bottom, and at the top we can have some value of FC maximum. These are your permissible values, FT, FC. These are your permissible values, maximum values we can have. Okay, so we can have the equation. Can you write the equation now directly? Can you write the equation at the top? What is the stresses at the top? For the first case, I would say that is equals to P naught by A, and this was your in this way that minus plus. So minus P naught E by Z. Third one is your moment because of the dead load, and that is equals to some FT. Then you have to ensure that FT is some negative value. So FT, okay. Second one is there, FC, P naught by A. This is F bottom. P naught by A plus K times P naught E by Z minus M dead by Z. That should be some value of FC. If you say this was your section. This was your according to these conditions. So we got the two equations. And similarly for the final stage, you are having some force of K times P naught at some eccentricity. So you can have this one, and this one. This is M all by Z. So let's write that. Third and fourth equation. So that's P naught by K times P naught by A plus that's minus K times P naught E by Z plus M all by Z equals to some value of FC. And fourth equation is that Kp naught A plus Kp naught E by Z minus M all by Z equals to F tensile at the bottom. So accordingly, then after doing some stuff there, so we derive final equations we derive, and we reach some values of equations such that final equations is Z required equals to Mach Ahmad by KFC. But we have to add here one more thing, that's minus FT. So that's your equation for the Z. And second one is there eccentricity. Its equation earlier was, what was the equation earlier? Mach Ahmad by Tukpo. But here our equation is getting changed to, this was for class 1. But your equation here is equals to E equals to Z times F2 minus F1 divided by 2 times P naught. So what is this F2 and F1? We have to see that also. So you have to replace this one now. So that's your equation for the eccentricity, and equation for the force. Equation for the force, Prestress force, that is equals to A times F1 plus F2 divided by 2. Earlier we had AFC by 2. We had AFC by 2, but in this case we had F1 plus F2 into A by 2. What's the value of F1 and F2? We have to see what is the value of F1 and what is the value of F2. Value of F1 is tensile stresses in the concrete minus dead load, dead moment divided by section modulus. And similarly, F2 is equals to F tensile divided by that left part of that stress K plus M all divided by K times Z. So these are your F1, F2. So let's take one problem based on these. Let's take one problem. That is the previous problem that we had earlier. So the problem is same. So in the final design that we got, I would say we got the beam that was 1300 and 800 dimensions. So this was your beam, and it's saying that for the same beam, for the same design, now I am allowing some tensile stress of, we are allowing some tensile stress of 2.5 megapascals. So this is allowed. That is, tensile stress is allowed some value, that is 2.5 megapascals. And what was the equation for Z earlier? That was ma command by KFC. So because of that, we had some value of Z. We had some value of Z. But in this case, I would say your value of this part is same. This part is same for this case, because this was your 5300 plus 0.8 md divided by KFC. This all is same. Now we have to add that equation. What is the equation for this one? What is the equation for this one? That's Z equals to Mach command by KFC minus FT. So minus FT, and you have to ensure that FT, we have to keep it in minus times that some megapascals. So we have to keep that also in negative. So minus times FC, minus times FT. So I would write here minus times FT. That's minus 2.5 megapascals. So because of this, your value, overall value will get decreased. So Z required would be lesser. So Z required would be lesser. Now if I calculate that, what should be my Z required corresponding to this condition? What should be my Z required corresponding to this condition? I would say if I fix that, let's say that I'm going to fix that dimension of 800, value of B, and we have some D required divided by 6, BD squared by 6. So I'm going to see what's my D required according to this condition. This condition, let's try to calculate now. So your D required is coming to be equals to 1188.8, 1188.8, 1188.8, 1188.8. No, this is not the way. This is not the way we have to do. Let me solve it. I'm going to write 5300 plus 0.8 into 0.8 into 1300 divided by 0.8 into 25 and plus 2.5. That's this one, and we have to multiply that 6 and divided by 800 and multiply of that 10 power 6 and root of that 1453. It should be bad. It's coming bad value. It's coming very bad value. So we need to check again. 5300. What is the equation? Actually, mark command, it's my negative value here. The value is here is negative. Mark command, it's negative here. It's minus. Sorry, it's minus. This is minus. So let me calculate again. 5300 minus 0.8 into 1300 divided by 0.8 into 25 plus 2.5 into 10 power 6 into that value of 6 divided by value of B equals to 800, and that root of that answer, that is 1191. So D required is 1191.63 millimeters, corresponding to this equation. So we have to go for the economical design. See, your D required here is 1300. So we can now select that. Let's go for 1200. Let's take the D as 1200. Let's take the total depth as 1200. Let's take the D as 1200. because we are allowing some tensile stresses. That means your depth gets to D required is lesser. Let's calculate for this one now. Let's try to see whether our equation, whether our Z required is satisfied. So that was your ma kamad by KFC. Ma kamad by KFC and minus of that FT. And that should be equals to BD cubed by 6, BD square by 6, BD square by 6, BD square by 6. That is D required. We want to see what is the D required we have based on this condition now. 5300, and we have solved that, I think. Yeah, we have solved that, and it's coming to be 11. It's now coming out to be 1188.88 millimeters, and that's, we say that's lesser than 1200, so that's safe. Okay, so finally I'm going to select down the dimensions of the beam as 1200 cross 800, and corresponding to that we are going to calculate now. We are going to calculate all those data that we have, all those data we have. So we have fixed the beam now. We have fixed the beam 1200 cross 800. Let's come to the equations that we derived. So we need to calculate these values. So first we need to solve for value of F1 and F2. Value of F1 and F2. Let's solve F1. F1 is equals to Ft. What is the value of Ft? We have permissible stresses in tensile, permissible tensile stresses, that is minus 2.5 megapascals. Minus dead. What is the dead moment? Dead moment is 1300 kilonewton meter divided by section modulus. What is the final section modulus that we have selected? That is BD square by 6. That is BD square. Yeah, 1200. We have fixed the dimensions at 1200. 800 cross 1200. So I would write this one as 1.2. This is 1.2 BD square by 6. This is meter cube. So finally F1 is minus 8.75 megapascals. F2, that is minus 2.5 divided by 0.8 plus m dead. Yeah, this should be MA. Your F2 is not m dead, it's MA. Sorry, it's MA. Okay, this will be value of 5300 divided by K times Z, 0.8 BD square by 6, BD square by 6. So accordingly, you have the units. Accordingly, you change those. This one is in megapascals, and this one is in kilonewton per meter square. So you can convert those, and finally your F2 is coming to be equals to 30.73 megapascal. So we have to substitute these two values, F1, F2, in all those equations such that I can write. Now let's calculate value of P naught. So P naught is equals to 0.8 into 1.3. So yeah, 0.8 into 1. Let's write in millimeters. 800 millimeters into 1200 millimeters of the cross section divided by 2 into stress 1, stress 2. That's minus 8.75 plus 30.73. So your P naught that you have to apply, that is equals to 10,550.4 kilonewton. This amount of Prestress force we had to apply, P naught. And what is the eccentricity we can get? Eccentricity can be solved as BD square by 6, BD square by 6, BD square by 6 into 2 into P naught. What is the P naught we have? 1055 0.4, 1055 0.4 into 10 power 3 newtons into F2 minus F1. F2 minus F1. F2 minus F1. Minus of F1. What is the F1? Negative times. Negative times 8.75. Negative times 8.75. So finally you can say eccentricity is coming to be equals to 359 millimeters. 359 millimeters. Now corresponding to these conditions that we have to check now the stresses at the two stages of the beam. At the two stages of the beam. Let's check the stresses now. Let's check the stresses. We had the same beam. We had that same I section beam that we have in the previous problem. Nah, this is not the I section. We selected the dimensions as rectangular. This is 1200. This is 800. And now I would say neutral axis is here. P force is applied here at some eccentricity of E that we calculated all that stuff. 359. Eccentricity is 359, and P load is acting here. P load we also calculated P naught. Let's calculate for the transfer stage. So I would say one of the stress is P naught by A. Second one is that P naught E by Z. P naught E by Z. Third one is there because of the dead load. M dead by Z. M dead by Z. So what is the dead load? Your dead load is getting changed because your WD got changed. That is 25 into 0.8 into 1.2. So dead load is getting changed, and we have solved that directly. Then finally, I would say that was your WD L square by 8, and all that stuff is same as per the class 1 condition. You can see that. So that finally, I would say that M dead by Z is coming to be 6.25 megapascal. M dead 6.25 megapascals, and P naught by A, its value is P naught by A value is equals to 10.99. This value is 19.74. So I can say stresses at the top is coming to be equals to positive, negative, positive, positive, negative, positive, positive, negative, positive, positive, negative, positive, 6.25. So final value of minus 2.50. And second one is that F bottom, that's 10.99. This is positive 19.74. Third one is negative. So net value of 24.48. Let's have the diagram. Let's have the stress diagram, final stress diagram. Final stress diagram is there. That's minus 2.50. And there is one more value of 24.48. So comparing them with the results of what we have. So your 2.50, this was also permissible. This is equals to permissible value in the tensile zone. I can say this is almost safe. We can say almost safe. We can say this is safe, and this is less than 25. So this is also safe. So I would say this is okay. We can say this is okay. And let's calculate for the second case. That's the final stage. That is the final stage. At the final stage, what we have? K times P naught. K times P naught. K times P naught. All that stuff. K times P naught. That means this part you have to multiply with 0.8, 0.8, 0.8, 0.8. And because of the dead load and live load, now we have the dead load and we have the live load here. So I can write here M all. So we need to solve for the M all. M all is coming to be 27.083. That's 27.083 megapascals. This is the effect of M all by Z. That's 27.083. 27.083. Let's substitute those values. Let's solve for those values. 27.083. 27.083. So your stresses comes to be equals to final values of one is your 20. Second one is that minus 2.49. And comparing with the original values, comparing with the permissible values, we have this 20, we have this minus 2.49. I would say this is lesser than as compared to the permissible 2.5. So this is okay. And this one is less than 25. This is also okay. Okay. So fine. We also need to calculate the area of the steel. What is the area of the steel we have to provide? Area of the steel. And that's a function of how much prestress force we have to apply and what was the permissible stress in the steel. Let's take the permissible stress in the steel was given to you as 1500 megapascals. 1500 megapascals, and calculate this area of the steel. So area of the steel is coming out to be equal to your P force was, what was your P force? That was 1055 0.4 kilonewton, and accordingly your steel area is 7033.6 millimeter square area required. So that's the end of this problem, and we can take the final one. We can have the final problem. That's the final problem of the design of the beams. That is the final problem. That's post-tensioned prestress concrete beam, and its dimensions is already provided to you. That is B is fixed from the problem itself. So we need to get the D, and we also need to get the P. So we need to get the D, we need to get the P, we need to get the E. So this is the thing we need to get. So we need to get these things. and you have this live load. You have this live load of W live equals to 25 kilonewton per meter, and the length of the beam is 12 meters simply supported. Stresses, permissible stresses in compression, concrete 17, permissible stress in tensile stress, negative 1.4 megapascals for the concrete, and stresses, losses, percentage loss 15%, percentage loss 15%. You have to say what is the minimum depth we have to provide, minimum depth required, and accordingly you have to get what is the P and what is the value of E we have to take. So I would say this is the class 2 type, class 2 or class 3 type, class 2 or class 3, class 2 or class 3 type. Now we need to say what is the equations we have, what is the standard equations we have. One of the equation is that Z equals to ma kamat by tukpo, yeah, ma kamat by KFC minus FT. So we know the value of MA. Yeah, MA can be solved as M dead plus M live. So let's solve the M live. M live is 25 into 12 squared by 8. What is the value of M dead? So because our D is unknown, so our D is unknown, let's keep it in terms of D, unknown D. So your D is unknown, your D is unknown. Let's solve for the section modulus. Can you tell me section modulus is equals to? Section modulus is equals to 240 into D squared by 6, and we can substitute here 240 into D squared by 6. And what's the value of dead load? What is the value of dead load? That is 25 kilonewton per meter cube into 0.240 into your depth of D is your depth of D, but you have to keep this depth in, meters. We are keeping the depth in meters. We are keeping the depth in millimeters, sorry. So if I'm keeping the depth in millimeters, so this one is your millimeter, but this is your meters. So let's say that D is in meters. And accordingly your dead load is coming out to be 25 kilonewton per meter cube into 0.240 meters, and D meters by 1000, such that it becomes yeah, I have to keep the D in millimeters. That's why we are going for this part, such that this final value is in, this final part is in meters. This is final value in meters. So your dead load is coming out to be 25 into 240.240. That is 6 times D. So let me try to add. This is 25 into 0.24 divided by 1000. So that's some value. That's 3 by, I would say this is 3 by 500, and this is D. So this is your dead load in terms of kilonewton per meter. And if I say what is the moment we can have because of this, what is the dead moment we can have because of this? That's WL squared by 8. This is WL squared by 8. 12 squared by 8. It's all in meters, kilonewton meters. It's all in kilonewton meters. So this value is, this is 144 by 8. So this is 0.1080 kilonewton meters. So this is your value of 1080 kilonewton meters into D. This is your value of moment, dead moment, 0.1080 times D kilonewton meters. And what is the live load moment we have? 25 into 12 square divided by 8. That's 450. So live load is 450. Live load moment 450 kilonewton meters. 450 kilonewton meters. So let's solve that. So let's substitute here. I would say this is your 240 D squared by 6 equals to ma. Your value of ma was equals to 450 kilonewton per 0.1080 D, and minus 0. Your loss percentage is 15%. Okay, loss percentage is 15. That means K value is 0.85, and your value of MD is 0.108 times D, and this is your ma kamat divided by KFC. What is the FC we have? Permissible stress in concrete, that is 17 megapascals, and minus of FT. FT is 1.4, that is negative 1.4. Negative 1.4. That's, see, the top values were having some values of kilonewton meters, and at the bottom we are having some megapascals. So accordingly you have to convert that all such that your d comes to be equals to, see, this is your equation, quadratic, d square, and this is linear, so you can have a quadratic equation. So d comes to be equals to 861. So I can say equation, one of the equations becomes finally 450 plus 16.2 d is equals to 625.6 d square, such that your d required is coming to be 861.2 millimeters. Now based on this one, I would say you can adapt to some value, because the problem was saying get the minimum depth of the beam, get the minimum depth of the beam. So we can select that minimum. Let's select that minimum value is equals to 870. That minimum value should be 870 millimeters. Now corresponding to this value, I would say what is the value of P naught, what's the value of eccentricity. Can we solve those? So eccentricity, for that we need to solve now F1, F2. F1, F2 we need to solve. F1, F2. What is the equation for F1? Equation for F1 we know Ft minus m dead by z. F2 F top by k plus m all by k times z. So substitute those values. Let's substitute those values. So I would say this is your, it was given to you as minus 2 point something. Tensile stress is allowable 1.4 minus 1.4 plus minus dead load. What is the dead load now? What is the dead load now? That is, what is the dead load now? I can have dead load. That is 0.108 into d. 0.108 into d. 0.108 into d. Value of d we have to substitute here. Value of d, that was 8. What was the d we got? 870. So that's 93.96. 93.96. So we can write here dead load, that's 93.96 kilonewton meters, and divided by section modulus of BD square by 6. BD square by 6. So this one is your in kilonewton per meter square, and this one is your in megapascals, and accordingly you can convert that into megapascals. F1 is minus 4.503 megapascal, and second one is that minus 1.4 divided by 0.85 plus m all. The m all is coming out to be, let's write that 450 into 450 plus 0.108 into that depth. What was the depth? That depth was 870 divided by, this is the m all, divided by z, section modulus of z, BD square by 6. BD square by 6. So finally I would say F2 is coming to be equals to, this one is in megapascal, this one is in kilonewton per meter square, and finally your F2 16.3196. so your P naught would be equals to, what is the equation for P naught? That is A by 2 F1 plus F2. So A1, what is the area of the cross section? Area of the cross section was 240 into 870 we have into 2 divided by area sigma F1 plus F2. F1 plus F2. So your P naught comes out to be equals to your force, Prestress force that you can have, initial Prestress of 1, 2, 3, 4 kilonewton. And your eccentricity can be solved as, eccentricity is equals to Z by 2 PO and F1 minus, F2 minus F1. And you can solve that one also. It comes to be equals to 255.4 millimeters. Thank you for watching this. All that stuff we have related to the design of Prestress concrete beams. Thank you. Thank you for watching. Thank you.